So in the last video of creep fatigue crack growth analysis, we modeled CT specimen in 2 dimensions based on the article by Ramirez et al. And so we have taken the material which is modified 9chrome 1 moly, and the test is performed in this article at 625 degrees Celsius, and the material properties are elastic modulus, Poisson's ratio, yield strength, tensile strength, and Norton's creep law constant for the steady state, that means the time dependency is 0, has been provided in this article. Then the loading scheme is based on this trapezoidal waveform. So load goes down to 0, then goes up. So the unloading time is UT, loading time is LT, and then there is a hold time, and then the cycle is repeated. So there are a few changes which I have done in this model, but this is just a basic model to, if you want to model something like this. So so the LT and UT time is 0.25 seconds, 2 seconds for 9chrome 1 moly, and the hold time, this article has tried for 60 seconds and 600 seconds. And they have used a node release technique, and these star points in this article shows the points where the nodes have been released. And so this is the kind of geometry they have modeled in 2D, and they have kept a very fine mesh size, and they have created this node release technique. And then here it says that modified 9chrome 1 moly steel at 625 degrees Celsius, the normalized element size near the crack tip was delta A divided by RF, where RF is the forward plastic zone size in this simulation, and the applied load was R is equal to 0.1. So when R is equal to 0.1, the minimum, so P max is 9 kilonewtons, so the minimum load will be 0.1 into 9, which is 9 newtons. No, it will be 0.9 kilonewton, so 900 newtons. And I do not know why this thing, then this cycle is going down to 0 here. So node release scheme tested in finite element simulation of creep fatigue crack growth. Method B was employed to produce the result in this study. So method B is release every 2 cycles at minimum load. So node is released after every 2 cycles at the minimum load. But minimum load in this waveform appears to be 0, but according to the text here, I think the minimum load will be 900 Newton. So that's what I have done. So how we have done that I will explain in a bit, and then we will proceed. So a few details in this model you can see in the last video. And so in the property module, so we have created this material which has the elastic modulus given in the article, and then plasticity, they have, what they have explained is that, so about the plasticity, they have said that they have modeled elastic perfectly plastic material with the yield strength equal to flow stress. So that means the average of 325 and 344, and then the yield strength value will be 0. So how do you model elastic perfectly plastic in Abaqus? Is you provide only one pair of points for yield stress and plastic strain, which will be an average of 325 and 344. But this causes problem because the convergence becomes an issue if you try to model elastic perfectly plastic material. So in order to avoid that, I have kept it from 325 to 344, which is the ultimate tensile strength, and I have done a linear interpolation of the plastic strain value, and plastic strain maximum is going to 0.4 approximately, but this I have not taken from any article, so I feel that, usually 20%, 21% is the elongation of modified nichrome-1 moly at room temperature. So I'm guessing that, if the yield strength is going down, the material is becoming softer, it will go to that extent. It might not go, but so for that you need to find out what is the percentage elongation at 625 degrees Celsius for this material, and then corresponding to that you get this limit, and then you can linearly interpolate, or you can interpolate in the way the stress strain behavior changes. So that was about the elastic perfectly plastic thing. Then in order to do the node release, what I have done is I have done some calculation from the data which is provided in this article. So for instance, here they have given the so this plot, so figure 9. So in figure 9 they have for 600 second hold time, the green line represents the dA by dN versus delta K. Okay, and you see that F max is 9 kilonewton, P91 is steel, CT specimen, R is equal to 0.1. So in order to do that, what I have done is I have taken the data from this linear line, so the FEM simulation result, which is the green one, and from the web digitizer. So we have delta K and we have dA by dN, and then from dA by dN, for if the number of cycle is 1, what will be the value of dA that I have calculated, and in order to produce that much amount of dA, how many elements will I have to release. So how many nodes will I have to release, how many elements will be out of the boundary condition. So I take 3 points where this number becomes integer 14, 15 and 16, and corresponding dA values, and then I linearly interpolate, and then so dA and dA by dN will be same because dN is 1, and then I plot these 3 points and linearly fit them using this equation. I create more values for dA, so how many number of nodes to be released, and then what will be the amount of dA for that. So then I'm trying to simulate the same dA by dN irrespective of whatever is the delta K, because delta K we will be measuring from or calculating from the ODB result, so the result of the finite element analysis. So I'm trying to keep the same dA by dN which Ramirez et al. Has used, and this we will do in these many steps. So how we will do, we will release we will release 12 elements, and then in the step 1, so after step 1, so in step 1 what we will do is that we will apply the load to maximum, and then it will come back to minimum. So one cycle will be done, and after that no, so what we will do is that in step 1 we will load it to P minimum value. So step 1 we will load it to P minimum, which is 900 newtons. Okay, and then the next cycle will start. So it's like in step 1 we will start from here, so minimum load here, and then we will in the step 2 this cycle will start. So it will load, hold and unload to minimum value, and once one cycle is finished, then we will release how many number of nodes, we will release 12 elements. Okay, so that this much amount of delta A is observed after one cycle. Then in step 2 we will release 14 more elements, then 15 more elements, 16, 17 and so on. Okay, and okay, so this is how we will proceed. So in order to do that we have to make 23 steps, and in 23 steps we have to be careful with the boundary condition. We have to create this much amount of delta A. So how I am doing that is by writing a small code in Abaqus scripting. So that is here. So I take this matrix where the number of elements to be deleted in its so released from the boundary condition is taken in this list, which is T element, and these are not required. So this was a previous code which I have modified, so these values are not required. So I will just comment it out. So and then we have this xc is the x coordinate of the crack tip, yc is the y coordinate of the crack tip, and this is 2 dimensions, so z coordinate is 0. B is a matrix which I will be using to deactivate some of the boundary conditions. So here in this loop, this step formation happens. So there are 1 to 23 number of steps which are being created. Step 1 is created manually, and so it goes from I plus 1. So step 2 and step 23, 2 to 23 will be created in this loop, and all these steps will be creep, so time dependent steps, so viscous steps, and maximum number of increment is 1000, initial increment is 0.001, and these are in hours. The time is in hours, and because these are in hours, we have changed here so the whole time, so the time of the step is, for instance, here. So loading time is 2 seconds, hold time is 600 seconds, so total becomes 602, and then unloading time is further 2 seconds, so 604. So this is one cycle, loading, hold, unloading, and this has been changed here in hours by divided by 3600. Okay, and in that term we have given the time step, which is, so the total time for this is 0.335556 hours, and we have provided an amplitude which will tell the model how the load will be applied. So I will show you that amplitude to you, which is here. So you see, at 0 time the load is 0.1, because the step 1 there is no creep deformation, only loading is happening, and then this is the loading time. So the load value goes to maximum, then this is the whole time, load remains to the maximum, then this is the unloading time, load comes down to 0.1 because R value is 0.1, and then it goes to maximum. So these are actually 2 cycles. So these are actually 2 cycles. So let me see. So we are breaking it in, so in each step we are going 2 trapezoidal cycles. Okay, so number of cycle is not 1, actually 2. So I will change this amplitude and I will delete these parts. So delete rows. Okay, and corresponding change I have to do here. So the actual timing will be, so the timing will be actually, so this is unloading, so the timing will be 0.167778 hours. Okay, so this is for the next one. Okay, so 0.167778. So that change I have to do here. So this will be simply divided by 2. So 0.167778 hours. Okay, so that is done. And then here what is happening in the second loop, we have the step name, and then there is a node set which is forming for the boundary condition, and this is the name of the boundary condition, and then history output we are creating, and but history output will have to change in any ways, and this is the mod assembly which is being called here. And then the node set is, so all the nodes from the instance has been called here, and then TT is a temporary variable which is just one of the values of this T element. So that means how many number of elements has to be deleted. So this is taking from that list, and then get by bounding box method is used to make the node set. So we start from the minimum value of the x coordinate. So that will be the present crack tip value minus a little distance, a very small distance which is smaller than the element size, and then maximum coordinate value is the end of the ligament. Y value will remain same because we are not changing anything in the y coordinate for the crack plate. So this node set is basically this one. So if you see, this is the node set, okay, and this is, so when you want to make a node set, you select this by dragging your mouse, which makes a box, and the same thing can be done by coding it by using get by bounding box command in Python in Abaqus script. Okay, so for instance, in this case the crack tip starts from here, so we take this as xe plus tt into the element size, and then it goes to a maximum value of x coordinate so that the whole ligament is covered. So and y coordinate, there is no extension because you are selecting only nodes on the same on the crack plane. So that's what we are doing there, and then this region selects that node set and the node set name, and then we apply the boundary condition, and in that boundary condition we are applying the y symmetry boundary condition. Okay, so this is y symmetric boundary condition because crack is symmetric along the y plane, and then we are creating history output for the node set which is j far. So we are going to history output create step, whatever is the name of this step. So this step is a variable, which means a step plus a string I plus 1, and contour integral j far, and we are creating here c type of integral, and then we are creating j type of integral, and that is it for one of the node set which is j far. But we will be doing it differently because this is not working properly, and then we deactivate the boundary condition which is created in certain node set, and then for the rest of the node set it is deactivated. So that I will show you here. So what happens is that when you release the node, so in one of the steps, let us say you said that this much amount of the nodes are under symmetry condition, so that is the ligament, and then you release one node. Okay, you release one node, so then you want only these nodes to be under y symmetry condition. So you have to deactivate the boundary condition which was created before, that includes all these nodes to be under y symmetry, because you are releasing this one. So you want this y symmetry boundary condition to hold only on that remaining ligament and not on the previous ligament. So you have to deactivate that. So if you go to boundary condition, so you create one boundary condition in step 2, and in step 3 that should become inactive. So it should become inactive after step 2, because in step 2 there is another boundary condition for the ligament, okay, and so on. Okay, so this is what we do using this code, and I will save it and I will show you how it works. So I will delete all these node sets which has been made previously. So delete, and then history outputs and everything will be deleted automatically. There are some boundary conditions which are created manually. So let me run the script again, and you see now the node sets has been created and steps has been created to 23, and we can check if the timing has changed. So we will go to one of the steps which is step 2, and in step 2 we have so let us go to step, and we select step 2 and edit, and you see that the timing is 0.16778 instead of 0.33, which was a mistake because it was counting 2 cycles. Alright, so that has been done. Now we go to steps, boundary conditions, and we check at the manual boundary conditions. So manual boundary condition is the first one. You see that is propagated in all the steps, and that simply says that, so it simply says that this loading point, which is the reference point here, that will not move in x direction, and this is valid for all the steps. And then we have another boundary condition which says that this should be only for step 1, so this is activated for all, so I have to make it inactive, so deactivate, and so it is deactivated for all the steps except step 1. And in step 1, if we look at the load value, so load value, so you see in step 1 we should go to 900 newtons, okay, so we are going to 900 newtons, and then from step 2 we should go to 9000, which is 9 kilonewton, and this will be true for all the steps. So I have to keep moving right, so that so I have to change in all these values. So okay, so this is propagated up, so that means it has become 9000, so it is okay. Okay, good. So now we are good to go, everything is done. Okay, and now we go to job, and then I have created a job which is trial, and then I write, so instead of that I will create another one, so let us name it trial 2, and then okay, and then I just write the input file for this, and okay, there are some problem in the history output from the code, so a little changes we have to do. So input file has been written, so let us open that input file, which is here. So this one, okay, so this one is the input file, and when I open it and I go to the end, it is so you see that in history output the j integrals has not been asked, so that part of code is not working for some reason, so I will have to do it manually for 23 number of steps. So what we will do here is, so this is step 1 and this is ending here, right, and after that what I will do is I will just paste a few lines which are these lines, so that I don't want, so I will basically copy and paste these lines here. So in step 1, just before the last line of the step 1, I will paste these lines: contour integral type j, contours 1, frequency 1, and the name of the node set is j10 millimeter, and this is j far. So there are two node sets, and the type of contour integral is j, and I will copy it and I will paste it again, and there I will change this to C integral, so type C, okay, and now I will have to paste these lines in all the steps, and frequency is 1, okay, so in each increment wherever the data is written, it will write the history output. So this is step 2, so I'll do the same thing, and then I will have to do it for all 23 steps. So I have pasted for all 23 steps these lines, and if we could delete these lines, probably the time taken by the simulation will be less, but I will not do that for now. So I'll just save this input file in a different name, so I'll save it to cfcg, and so cfcg node release Ramirez, so I'll just write Ramirez, and I'll write 1 and then .inp, and then I will run this file. So we go here and import model from the input file cf Rami. So cfcg node release Ramirez 1, this is my input file. Okay, continue. I'll provide some memory to this, maybe 30% is okay, and parallel I'll put it, let's say 30, MPI, okay, and I hope the work directory is the same directory, yeah, and then submit it. So this has been submitted, and let us see when it is when the solution comes. So now the job has finished, and it took a while in the pre-processing of the input file because we have placed a lot of history output requests in 23 steps. So all those checking in the pre-processing takes a lot of time, but once the calculation starts, it doesn't take much time for the calculation to come up. So let us look at the results now, and from the very beginning, so if we go to initial stage, it's that, and then the crack is here. And if we look at the plastic strain, so not coming up much because it's 900 there at step 1. In the very beginning, it's very low. So, and as we proceed, we have a little bit of creep there. And now let us play the video of the deformation, and you see that the crack is initially here. And let me put a limit, lower limit to be 0.0001, and apply. So that is higher. So specified, okay. So and this could be 1. So apply. So see, this is there, and I believe it has gone here now. So the crack has gone here, and now it's growing in each step. So we have to increase the, what do you call it, the deformation factor, so that we can see clearly the crack opening. So now you can see how the nodes are getting released in each step, and the crack is growing. Okay. Okay, so it looks okay. It looks okay. And now let us look at the history output which we requested for. So we have C integral for J10 node set and C integral for JFAR, and we have J integral for these two. So if we look at C integral for these two contours, and if you want to see how these J10 and JFAR are, so let me show you the node set. So J10 is here. So J10 is from the initial crack tip a little bit after, so before it takes 10 millimeter in the forward direction. So this node set, if we go to the last stage, so this is our 23rd step. Our crack tip still is inside this contour. Okay, so J10 is this, and J far is is a remote far field contour. So this is on the boundary of the specimen. Okay, so here it's not important to cover everything because there is no deformation here. It's better to leave the hole out. And so let us now look at the history output and C integral. So we'll save these two as CT and okay, and let us now look at how they look like. So we'll select these two and we'll plot them, and you see that it is initially there. So these jumps are there when you have change in the step, and once the step changes, the C value also changes a little bit. So there are two values. One is for so the purple one is for J far node set, and the other one is for J10 node set. So you see here, before time is equal to 0.504, these two are having a very close value, and here this weird jump is because there is a node release, and after that they again are coming up, but there is a difference, a bigger difference between these two, and then they probably come very, very close, almost equal, and then again they start to behave in the same way. Okay, so at each step you see there is a change, there is a jump, and then the CT values come up. So we can take these CT values for different crack lengths, and because our dA by dN is going to be, I hope it's not same, it shouldn't be same, because we tried having increment in dA by dN with our crack length. So we want to change dA by dN, and we want to see how is the relation with the CT value. So step one, if we look at step one was for 0.33559. So it went for 2 cycles, nothing happened there. Basically it just applied a load of 900 newtons, and there was no amplitude given, so it is straight away instantaneously applied that minor load. So that much time it took, so that is okay. And after that, in step 2, it took 1 cycle, so loading, unloading and holding of 600 seconds, and after that 1 node was released, or no, so 12 elements were released. So okay, so I think there was a mistake, because the number of steps should be counted not from XC but from XC plus the previous value, because this 15 number of nodes are to be deleted in this step, not just 1, right? Or is it? So delta A for this step is going to be how much? Delta A is 0.75, but this is from the very beginning, so that should be the delta A. But in each step dA changes, right? Yeah, okay, so yeah, so it could be okay, I think. So in step 2 it goes for 1 cycle, then node released, step 3, step 4 and so far that happens. Okay, so now we need to analyze the results, and we need to find out what is the value of C integral, and then we have to calculate dA by dN value, and then with dA by dN versus CT plot, and then we'll have to also see what is the value of delta K, what is K opening and all those things. Okay, so we'll do that. So there will be some changes in C value. So first step went for 0.33 time of 0.33. So that is there. So here the step is changing. So here the value of CT was 2 into 10 power minus 5. Then in the next step, which ends at 0.33 plus 0.167. So that will be approximately so 9, so 0.5 approximately. So here. So here. So this is where step 2 is changing. Step 2 is ending, and in step 2 you see the value of CT is 1.5 into 10 power minus 4. So from 10 power minus 5 it has gone to 10 power minus 4, and then it goes to 10 power minus 3, and then it goes to, it remains in, so no, it goes to 0.2 also. No, 0.2 is happening at the jumps. So that then it goes to 10 power minus 4 again. It goes back to that value, 10 to the power minus 4. So it remains at 10 to the power minus 4, and a little bit 1.3, 1.2, that kind of values are changing. So that needs some analysis, post processing, to understand the results. And if we look at the J integral values, and let us see how they change. So I'll just plot for, no, I can plot for both of them, J10 and J far. And if you look at the values, so the J integral looks like this. So in the first step there is a huge node release, because 12 elements are getting deleted in one go, and then small number of nodes are being released in each step. So the J integral is showing this kind of behavior, and in each step you will see that the J integral is actually rising to a value and then getting saturated. Okay, because there the load is held on, and because of the creep deformation the J integral is changing in that way, and then it changes again to a different value because the node is released, and this is why we have this kind of behavior. So we need to plot J versus delta A. So for each step you will have a value of J and you will have a value of delta A, and that we can use for our analysis. J versus delta A, we can convert that to, so delta J, delta K, we can convert that to delta K, and delta K versus dA by dN also we can plot. So I hope this gives you an idea how to start or begin with the modeling of creep fatigue crack growth using the simple idea of node release. And that's it. Thank you.